All right, let's dive right in. Today, we're peeling back the layers on something truly remarkable, the STELOS system. And this isn't just about some new piece of tech. What we're looking at here is the architecture of a whole new reality, engineered from first principles by Kavhanna. We're going to deconstruct it, piece by piece, to really understand the profound logic that makes it tick.
So, here's our plan. We'll start with the big picture, the new architecture. Then, we'll get into the three core pillars, the thermal engine, the atmospheric interface, and the conduit of power. And we'll wrap up by seeing how it all comes together in what Kavhanna describes as an unbreakable synergy. Okay, first up, a new architecture. This is really where we need to start, because Kavhanna's work isn't just an improvement, it's a complete shift in how we even think about energy. The idea here isn't to go find some source and tap into it. No, it's about orchestrating a flow of energy that's already there, all around us, right in the atmosphere.
So what's the fundamental purpose? It's actually incredibly elegant and singular. The whole point of the STELOS architecture is to take the ambient, scattered heat in our atmosphere and transform it, concentrate it, into a focused beam of electromagnetic energy. You can see how this immediately takes us way beyond conventional thinking. It's a whole new playbook.
The system itself is called STELOS, which is shorthand for Conversión Térmica Atmosférica, or atmospheric thermal conversion. And what it does is, well, it's designed to tap into something that's always been there, but that we've mostly ignored. The natural temperature difference, the thermal gradient, between the air down here at the surface and the much colder air way up in the higher atmospheric layers. And look, this isn't just some idea on a whiteboard. Kavhanna built this on two core design principles. First, it had to be modular, meaning it's designed to be scalable, something you can build out progressively. And second, it needed to have environmental robustness. It's engineered to work continuously, reliably, even when atmospheric conditions are all over the place. We're talking about practical, real-world engineering here. All right, on to the first major component, the thermal engine. You can think of this as the absolute heart of the system. This is the spot where a simple difference in temperature becomes actual, usable power. And to understand it, you have to grasp what Kavhanna calls the first law of this architecture. All power is born from difference. It's such a simple but profound idea. For this engine, that difference is heat. It's a thermal difference. And that single principle is what underpins everything else. So how does it work physically? The process is called thermoelectric conversion, and it's based on something called the Seebeck effect. It's actually pretty straightforward. Imagine you have a special material. If you heat up one side and keep the other side cold, electrons literally start moving from the hot side to the cold side. That flow of electrons, that is an electric current. It's an incredibly direct, fundamental way to generate power. And get this, these numbers you're seeing, these aren't just theoretical goals. These are the actual validated parameters from Kavhanna's work. The system operates on a steady thermal gradient, that's the temperature difference, of 50 Kelvin. The thermal electromagnetic efficiency is 3.84%, and then you have this figure of merit, or ZT. ZT is basically a scorecard for how good the material is at doing this conversion. A ZT of 1.4, that's incredibly high. It tells you we're dealing with some seriously advanced material science at the heart of this engine. So let's walk through the flow, step by step. 1. A hot surface down at ground level, around 300 Kelvin, just soaks up the ambient heat. 2. Way up at altitude, a cold surface radiates that heat away into the cold sky, which is at about 250 Kelvin. 3. The thermoelectric modules are sandwiched right in between, bridging that temperature gap. And 4, what's the result? A steady, predictable flow of direct current, or DC. Okay, that's great, but it brings up a really important question, right? How in the world do you reliably create and then maintain that 50 Kelvin temperature difference? Well, that is the job of the second pillar, the atmospheric interface. This is the part of the system that actually engineers the very conditions the engine needs to run. I mean, you can think about it like this. The thermal engine is, well, it's an engine. And without that stable temperature difference, the engine has no fuel. It just sits there. The atmospheric interface is the system that delivers that fuel reliably and consistently. And the way it does this is through this really elegant duality. Down low, you have what's called a superior thermal collector, which is engineered to be amazing at soaking up heat from its surroundings. Then, up high, you have an inferior heat sink, which is designed to be equally amazing at dumping that heat into the cold upper atmosphere. It's like a perfect push and pull system, a collector and a radiator, two sides of the same coin, working in perfect harmony.
And what's the result of all that? This, a stable, engineered thermal gradient of 50 Kelvin. This number isn't an accident of the weather. It is a constant potential difference that is actively and precisely maintained by the architecture. You could almost call it the unwavering heartbeat of the entire STELOS system. Okay, so we've got our temperature difference, and our engine has turned that difference into a steady, direct current. So, now what? How do we move that power? That brings us to the third and final pillar in Kavhanna's design, the conduit of power. This is all about taking that raw electricity and turning it into something we can actually transmit. The chosen method here is microwave transmission. So you take that steady DC power coming out of the engine, you feed it into this subsystem, and what it does is convert it into a very focused, coherent beam of electromagnetic energy. Microwaves, to be specific. Now the power is ready for precise, wireless delivery. And again, the specifications are just as rigorous as everything else. We're looking at a central frequency of 2.4 gigahertz, which is pretty standard, but check out this pointing precision, plus or minus 0.1 degrees. That's incredibly accurate. And then there's the efficiency of converting that DC power into the radio frequency beam, 85%. That is an incredibly efficient way to channel power.
And this chart, this really drives home that core design principle of environmental robustness we talked about earlier. Look at this validated data. Of course, it works best in a clear sky. You get about 66% transmission efficiency. But even in heavy rain, it's still operating at over 43%. This thing isn't a delicate lab experiment. It was explicitly engineered to work reliably out in the real world with all its messy weather.
So we've looked at the three individual pillars: the atmospheric interface, creating the gradient, the thermal engine making the current, and the conduit of power forming the beam. But the true genius of Kavhanna's work isn't in the parts, it's in how they come together. This is the final piece of the puzzle, the unbreakable synergy.
But that's the big question, isn't it? How does this architecture manage to fuse these three distinct systems into one single, unbreakable, codependent machine? What's the secret to that perfectly elegant logical loop?
Well, the answer is in its flawless logical loop. It's like a perfect chain reaction. The atmospheric interface creates the stable thermal gradient. That gradient is the exact input the thermal engine needs to generate a steady direct current. That current is the exact input the conduit of power needs to create a focused RF beam. You see? Each subsystem's output is precisely the input the next one needs. There's no waste, no gaps. It's a completely closed, self-reinforcing system.
And we can even see this synergy in the numbers. The total efficiency of the system isn't just an average, it's a product. You start with the thermoelectric conversion's 3.84% efficiency. Then that gets multiplied by the transmission efficiency, which we'll call an average of 66.4% here.
And what do you get? 2.55%. And let me be clear, this isn't some theoretical best-case scenario. This is the validated, end-to-end, real-world efficiency of the entire STELOS system. It's the hard number that proves the synergy works. The whole is quite literally the precise product of its parts.
Which brings us to this final, powerful quote from Kavhanna's own work. An architecture where energy is not found but orchestrated, a closed loop between matter and force, governed by the laws of a new reality. It's a profound way to think about it, not just finding energy, but conducting it like an orchestra, all based on a new set of rules.